Hello, welcome. In this short video, let us look at some examples illustrating how to solve for unknown variables in equations involving normal random variables of arbitrary mean and variance using standard normal distribution tables. That is, we want to solve for unknown values of x, probability of x less than x equal to a. This we want to solve for the unknown value x in these types of equations. So to start with, we consider the following equation, that is probability of x greater than small x is equal to 0.5. We have random variable x that has a normal probability distribution with mean 10 and standard deviation equal to 2, that is variance equal to 4. And probability of x greater than a value can be rewritten as 1 minus probability of x less than or equal to that value from probability theory, of course. So this is equal to, and now this can be transformed into standard normal probabilities of standard normal random variable by simply transforming the values on both sides of the inequality. That is probability of x minus 10, that is x minus mu by sigma, that is x minus 10 by 2, less than or equal to a small x minus 10 by 2 is equal to 0.5. This basically means that probability of z, this is equal to z, that is the standard normal random variable z, which has mean 0 and variance 1. So this is probability of z less than or equal to x minus 10 divided by 2 is equal to 1 minus 0.5, that is 0.5. From normal distribution tables, we can clearly see that at value of z equal to 0, we have 0.5. That means x minus 10 divided by 2 is equal to 0. That is, from the table we know that probability at 0 is equal to 0.5. So x minus 10 by 2 should be equal to 0. That means x equal to 10. So the solution to this equation when x is a normal random variable with mean 10 and variance 4 is x equal to 10, which basically makes sense because at the value of x equal to 10, the area under the curve is 0.5. Our area under the probability density function, in this case normal density function, is 0.5. That is what we see here. Let us look at another example. We have probability of lowercase x less than the random variable x less than 10 is equal to 0.2. So given this equation, we want to solve for the unknown value x. This can be accomplished by using the formula probability of a less than x less than b is equal to probability of x less than b minus probability of x less than a. So that is probability of an interval is equal to the difference between the probabilities at the extremes. So we have, this implies probability of x less than 10 minus probability of x less than small x, or the lowercase x, that is unknown value, is equal to 0.2. Now again, by using the transformation to standard normal random variable, we have probability of x minus 10 divided by 2 is less than 0 minus probability of x minus 10 divided by 2 less than small x minus 10 upon 2 is equal to 0.2. Clearly, this is equal to probability of z less than 0, and this is equal to probability of z less than x minus 10 divided by 2, and this is equal to 0.2. So this is equal to phi of 0, where phi is the cumulative distribution function for normal random variable. So this is phi of 0. This is phi of x minus 10 by 2. That is the value of the cumulative distribution function for the normal cumulative distribution function at x minus 10 by 2. Then this is equal to 0.2. From the table, clearly this is equal to 0.5. Here, at z equal to 0, the probability is 0.5. Therefore, this is 0.5 minus phi of x minus 10 divided by 2 is equal to 0.2. Remember that phi is normal cumulative distribution function, that is normal CDF. Usually you calculate this value as phi of z, where z is the value or the location at which you want to find the value of CDF. So this implies that phi of x minus 10 upon 2, that is by simple algebra, we know that phi of x minus 10 by 2 is equal to 0.3. Now we have to just look at the table. and locate the value 0.3. The value 0.3 is right here. So it should be equal to minus 0.5 minus 0.02. That is, it should be minus 0.52. Minus 0.52. That means x minus 10 by 2 is equal to minus 0.52. That implies x equal to 10 minus 2 times 0.52, which is equal to 8.96. Now let us look at another equation, that is probability of minus x less than x minus 10, that is the random variable x minus 10 less than small x or lowercase x, is equal to 0.99. Now this random variable can be transformed into standard normal random variable by simply dividing with the standard deviation, that is 2. That is minus x by 2, probability of minus x by 2 less than z, that is where z equal to x minus 10 by 2 less than x by 2 is equal to 0.99. And for a normal random variable or for a normal distribution, this value, that is probability of minus a less than x less than a, is equal to probability of x less than a minus probability of x less than minus a. But probability of x less than minus a is equal to 1 minus probability of x less than a. Therefore, probability of minus a less than x less than a, that is probability of an interval from minus a to plus a, is equal to 2 times probability of x less than a minus 1. So by using this identity, we have 2 times probability of z less than x by 2 minus 1 is equal to 0.99. That implies phi of x by 2 is equal to 1.99 divided by 2, which is 0.995. From the table, we can clearly see that can be seen at this location, that is 2.58. So the value 0.995 can be located at that is this row 2.5 and column is 0.08, this value. So it should be x by 2 should be equal to 2.58. That implies x equal to 5.16. Thus, we can solve for a single unknown value or single unknown parameter in equations that involve random variables that are normally distributed with arbitrary mean and variance using standard normal distribution tables. Thanks for watching.